Okay. Okay, so I'm pretty sure we're recording. I think that's what this little red button does. Is the quality still good for you guys as well? Because I know sometimes my pathetic internet connection makes it hard to.
Yeah, it's good.
Yeah.
Okay, that's a first. Alrighty, so first review session of the semester. Here we go. We're just gonna go through the teachers' lectures on this one. So let's see.
Why are they so
then-
dense? Like the PowerPoints.
He does move pretty fast through them. That I will say.
It makes me so mad. I just don't write anything down.
No, you're fine. I totally get it. Let's see. Okay. So with physics 2, it looks like the primer for all of it, and what we're really doing is having to do with electricity and magnetism. So that's chapter 22 of the textbook that we're using that I'm going to be receiving tomorrow, actually. So I'm pretty excited for that. What we want to keep in mind is that in classical physics, mass and, well, the two fundamental properties that determine interactions between objects is mass and electric charge. This is kind of just like fundamental, just, physics concepts, I guess. What kind of interactions do we know? Gravitational interactions. We all know the apple falling on Newton's head story. Force of gravity. I'm assuming this is force of gravity. I just kind of want to get to one of his first example questions here. Let's see, which I think if we check out the notes. Okay, actually, there's a few things here that are pretty important that are gonna be seen later on. So we will, in this class, we just assume that electric charge is a physical property that causes electric forces. We are not going to go into the details of like the why and things. I think he said like, so we just assume that objects always attract each other through gravity. So similar to that, there are two kinds of charges. We'll just kind of see them as like charges and opposed charges, where they can attract or repel. Positive and negative, 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 positive, positive. This is pretty, we all know this, opposites attract. Benjamin Franklin, who was a very great, what is it that our professor called him? A great politician and physicist and everything.
Nice guy.
Nice guy, good person. So really, one of the things also that we want to keep in mind is that with an atom, electrons obviously are negatively charged, protons are positively charged. It is easy to remove the first outer electron, and with each subsequent electron that you remove, there is more energy that is required to do that. It's like exponentially more. So also forgive my voice. I am a little bit sick today, I think. So I'm sipping on my water here. So here's one of the things that's most important is this chart here.
I don't know if anyone else, I'm not seeing your screen, I don't think.
Oh, are you not seeing my screen?
I don't know. I'm on my phone. So that
I
might
see
be why.
it.
Try swiping on it. Yeah.
Try swiping on it.
Like sometimes you have to look at like other, like it's weird. Zoom on the phone is very not good.
Oh, okay. I got it.
There you go. So you can see my screen all good. Alrighty. Okay. So now we're going to look at how charges are quantized. So this is kind of when we start getting into kind of the what's the word I'm looking for? Like what represents what amount of numbers or whatever. So an E is just a constant charge of coulombs, I think is how you pronounce it. So an electron is a negative E charge, which is going to be your default 1.6 times 10 to the negative 19 coulombs. Because it's negative, that would be negative. Your proton is the exact positive. One of the things in the textbook, it said it's pretty cool that a proton and an electron, despite being wildly different in mass, have the exact same charge. So that's pretty cool. Now, the thing is, there's a positron. We haven't really referred to this one too much so far. In some of his later notes, he has something called an anti-electron, which seems to kind of, well, you'll see it later in the notes, but this right here is very important. So you want to kind of have this highlighted in your notes, the kind of standard electric charge.
Do you have to memorize that?
No, I talked to him today after class, and the professor said that constants and things like that will be given to you as you need on the exam.
Okay.
I think he said that applies to equations as well, but I don't want to like tell you something and then,
Well, in the
that one I'm a
syllabus
little
it says
iffy
we
on.
get an equation sheet, so
Oh, okay. Then go by the syllabus on that one, definitely.
But do we also make a cheat sheet?
Yeah, that's
that
the equation
I'm
sheet. We have to make our own formula sheet.
Oh, there you go. Okay, that's good.
But like to what extent,
Well, the front page, right? Is that what it is? Like just the front page?
yeah, because he gave us that whole lecture about like a book and the numbers
Yeah.
or something.
He said magnifying glasses are still acceptable, so maybe
Really?
that magnifying glass story, he said that he'll still allow it.
That's so funny. Okay. That's good. I like that. I'm probably gonna try to do that. Okay. Anyway, I guess moving on. This is kind of what we're still kind of covering theoreticals in this sense of like, hey, or foundational things. So electric charge cannot be created nor destroyed. Basics of energy. In this example, he's talking about, these diagrams. You see, you have anti-electron. It is possible to create charged particles in high energy processes, but they are created in such a way that total charge doesn't change. Charge is really conserved. These two cancel each other out, you know what I mean? But you're, in a way, I guess, creating something out of nothing. Continuation of the charge quantization. You have a macroscopic object that has a net charge. So in this instance, this equation, what it's saying is you have your net charge is equal to the number of protons minus the number of electrons. And the constant here is the Coulomb's, I don't really know what's the word that the Coulomb's constant, this right here. Okay,
that's how many, that's the charge of an electron. The E means an electron.
The charge. So what you have here is the number of protons times the charge of an electron, because they have like charges, and then you have minus the number of electrons, and that's going to give you the macroscopic net charge of an object. Obviously, if you have more electrons than protons, this number is going to come out negative. And if you have more protons than electrons, this number is going to come out increasingly positive. And that's how that works. So like he says, most macroscopic objects have an equal number of protons and electrons, meaning that Q would be 0. Q in this instance is our net charge. Charged object. Charged object has an unequal number of protons and electrons. Notice that an object's charge is always an integer multiple of E. Yes, that is very true. So in this instance, I'm assuming we wouldn't, unless you want a gross net charge, you would plug in the value for E. If you just want a kind of cleaner version of it, you would just keep E as like a variable, solve this, and then keep that as like 7E, so there you go. This is called charge quantization. Yeah. Then we start kind of skewing into ionization. So the process of removing an electron from the electron cloud of an atom or adding to is called ionization. That can cause an atom to be positively or negatively charged. Most electrons in an atom are bound strong to the nucleus, core electrons. Few electrons can be relatively easy to separate from the atom. Valence electrons. Oh, a throwback to chemistry. Solid materials can be considered a collection of ions, nucleus plus core electrons, and valence electrons, just electrons, which can move through the material. this was pretty wild to me to kind of read, and he has a bit of a better example down here when he talks about conductors and insulators. So some electrons are free to move through the material, copper, silver, aluminum, gold, iron. Importantly, it takes much energy to remove electrons from materials. And then insulators are electrons that are strongly bound to nucleus, so it is very hard to make electrons moving. Rock, salt, glass, ceramics, plastic. So here you kind of have two example diagrams. In this instance, you have, I believe this is sodium and chlorine. So is this sodium chloride or something?
Yeah, that's so.
Yeah.
Yo, okay, there we go. Thank goodness. It's been so long since I've taken chemistry, so we're celebrating. There's something here when we talk about insulators and things. For me, it's mostly conductors was really fascinating, but insulators, pretty straightforward. It insulates things. Tightly bound electrons, tightly bound atoms, not really free to move. Charging an insulator by friction leaves patches of molecular ions on the surface, but these patches are immobile. This is, I mean, think about it, right? This is why we wrap, wiring in rubber and stuff. These things are very bad at conducting electrons. And this was a cool one. So conductors and metals, the outer atomic electrons are only weakly bound to the nuclei. So the outer electrons become detached from their parent nuclei and are free to wander through the entire solid. So the solid as a whole remains electrically neutral, but the electrons are now like a negatively charged liquid permeating an array of positively charged ion cores. That is crazy. It's almost like electrons are acting like a kind of free-floating fluid. I think that's really cool. Science, exactly. Magnets, how do they work? I have no idea, bro. That's awesome. All right. So this kind of just continues on what we were just talking about: charging by contact, charging by induction. These are not super core to what we've been going, but let's see if we can. Oh, there's no example question here. All right. Let's see what I have on my notes for the first day. Okay, not too much, but all right. Let's go on to the next lecture, because I think the next lecture does have some example questions.
Yeah, I really want to talk about Coulomb's law. That equation is like really giving me like trouble.
Absolutely, we will. Let's see. Oh, Coulomb. Oh God, yeah. Okay, now I see it. Okay. Lecture 2, electrostatics. This is pretty important. So one of the things we want to consider is that not all objects induce electromagnetic interaction. Two kinds of charges, positive and negative. All charges are come from electrons and protons, except for high energy processes. Anyway, so we're going to move on to determining the electrostatic force as a function of distance between charges and magnitude of the charges. I think this is actually pretty interesting in terms of like when he talked about this, it reminded me a lot of like the story of when like atoms were like first being discovered. I think there was some scientist that would like shine a laser through like a thin sheet of gold, like foil or something. And sometimes some of the atoms would reflect. That was such a long time ago though,
Yeah,
Oh, okay. So someone knows what I'm talking about.
Yeah.
Okay. So Coulomb's law. Yeah. Yikes. So basically what we want to take in, what we kind of want to think about here is you have the equation describes the interaction between point charges. So the point charge approximation works when the size of a charged object is much lesser than the distance between charges. And I think in this instance, he talks about the relation between the electrostatic force and the distance. And then this kind of plays into how an electrostatic charge can be greater than the effect of gravity, in a vacuum. So let me see what notes I have here.
What is the R12 with like the hat on it? Like, what does that mean?
So this right here, yeah, because I guess it's in relation to a vector, just because this is a force vector. So this, I wish he had this a little better kind of shown, but it looks like this is exerting a force on Q2, which is then, this is the net force vector. So what we want to kind of take into, let me just kind of write down the notes that I have here. Okay, so we have, I'm just gonna write it CL. This is gonna be Coulomb's law. This is, so we have the function, it's gonna go F 1, 2, let me zoom in a little bit. And then we get equals K. So K is actually a coefficient of proportionality, is what I have written here. I think I remember him vaguely saying that in class. That is usually, I believe, a given constant.
Yeah.
Okay, thank goodness. Alrighty.
He
R
said he'd give
squared.
it to us too, but I'm not sure if like that was like sometimes professors say that and then they don't. So
Yeah, that's true. Okay, so this right here is going to be a unit vector.
but like
My
what does that
goodness.
mean?
Unit vectors are pretty good for let me think here. Let's see.
The
let me,
unit
like,
vector
fact check
just
myself.
means that the magnitude will always be 1, but that's mainly just to show the direction. So like what he did today was we were treating the point like a positive proton, right? And if it was going towards the charge, it was a positive R hat, and then if it was going away from the charge, it was a negative R hat.
Yeah, this is kind of the equation for a unit
So-
vector.
In like the example on the slides, it was positive because it was going towards like the force was acting towards the
In-
charge.
Yeah, that
In
point.
the drawing in this thing right here,
Oh, like I was talking about how we never really used the R hat until like today. And then the reason he did that was because if it was going towards the charge, it was positive, and if it was going away from the charge, it was negative. But R hat will always be 1 because it's a unit vector.
yeah, and that's the thing, is also like, and we'll do an example that kind of takes this, which is the in the homework. But the positive and negative direction is generally relative to how you frame it as well. I know we did a lot of that in physics 1, but for example, in the homework, we have a question where it says like, we have a table. Oh, okay. We have a table like this. Okay, just imagine these are straight lines. Y and X. And then you would have, like, for example, say you have I don't know, this is a negatively charged particle, positively charged, and then you have a positively charged down here. And then it would ask you, what is the net force on, this is Q2. What is the net force on Q2, right? And so what you would say is, okay, well, this positively charged particle is exerting a repulsive force on Q2. And then this negatively charged, it's kind of pulling this, so it kind of the negative wants to pull the positive. So you would have a positive force in the positive Y direction,
Whoa.
So you're saying the R like hat thing would be positive in both of those cases then?
Yes, I'm pretty sure. Just because I guess I've never kind of seen this like in the laid out like this. The way I will do the work that I did on the homework in a bit. I just kind of wanted to get through the lecture notes first, but I could show you kind of the thought process on this. But yeah, so in this instance, it's a positively kind of what's the word I'm looking for? I guess pointing vector,
So in
and
this scenario, like just like talking through what you do, you'd find the charge on like the bottom one and the middle one, or the force from the bottom one to the middle one, and then the force from the middle one to the top one, and then you like add those together.
Yeah, basically. The way here, let me kind of pull out my notes here, my homework notes. Yeah, okay, here, let's do it as an example question then. Hold on. I'll just kind of create my own question here.
Well, can we just do the one that was on the homework? Or
I was gonna do one like that, but I don't know what the rules are on working on the homework together yet. So I'm just gonna kind of take heavy inspiration from a question I happened to see online.
right.
So what we're gonna do is we're gonna have, and this is related to this, thank goodness. So here's how it's gonna work, right? So we have a particle here. This particle is gonna be called Q1. Actually, let's go like this. Actually, no, I'm gonna keep it. Q1.
That was a pretty nice line.
This one actually worked out a little bit, so I'm pretty happy with it.
Good one. I don't know. It's a little
Q2,
wonky.
yeah. And then we have Q3 here. This is the positive X and the positive Y direction. Now, oh dear. Quick question. Oh, Jesus. How many of you guys have taken Calc 3 and Physics 1 by any chance?
Me.
I'm in Calc 3.
You're in Calc 3? Okay, so you
Yeah.
will see a lot of, it's vector calculus is Calc 3, so you'll see a lot of that.
Oh, yeah.
Okay. Y'all have obviously taken Physics 1 to be in this.
Yeah.
Okay, so here's what I'm gonna say. So we're gonna find the magnitude of the net force on Q2. I'm just gonna shorthand it. I'm gonna say mag of force on Q2. All right, so here's what's given. The charge of Q1, Q2, and Q3. So here's what we're gonna do. I'll write it down over here in blue, because I like blue. So Q1 charge is going to be, let's say, I'm going to say negative 2.0 times 10 to the negative 7 coulombs. Charge of Q2 is going to be,
Just to confirm for the homework, do we have to do sig figs?
yes.
Ugh.
I just punched it into a sig fig calculator. This one's going to be 4.0 times 10 to the negative 9 coulombs. And then Q3 is going to be negative 1.6. No, not 6. 8 times 10 to the negative 10 coulombs. So these are the charges, right? Now, let's say that the distance, this is a co-equal distance right here, and then you also have this. This is going to be your D. Your distance is going to be 2.5 times 10 to the negative 3 meters. That was a 3. Why does it keep doing that? 3. Does that make sense? We all good here?
Yeah.
So just kind of glancing at this, we'll see here that Q1 is a negatively charged particle. Q2 is a positively charged particle. And then Q3 is a negatively charged particle. So we don't have like similar direction vectors in this instance. This particle is being pulled in 2 different directions. It's being pulled by the Q1. So this is going to be the Q1 force. And then we have a pull from the second Q3 particle, right? It's just a matter of which side is going to win this tug of war. So that is where we consider what's called, what I have written in my notes as the net force equation, which goes like this. I hate the red look, so we're going to go with like purple. I like purple. Okay. The net force equation is going to be a fun one. This is how it's going to work. We're going to have force. That's a nice purple. Okay. Force is equal to the K constant times, and then this is going to be Q1, Q2 over R squared. And then this right here, we have N hat. This is your kind of net force vector. Now, actually, this is something from the second PowerPoint here that we were actually just going to review. What is K? This is a constant here. So I'm just going to write it here. We're going to look at it together here. K is actually in Coulomb's law, 9.0 times 10 to the 9th. I think this is Newton's meters squared divided by Coulomb. It's a complicated one, right? So I'm just going to move this to the side. I'm going to write it down. So this is going to be 9.0 times 10 to the 9th. And then this is going to be Newton's meters squared over Coulombs squared. Right? So let's think about this, right? Now, this is kind of where it's funny because I get a little bit of PTSD from physics 1. And I believe this is where we kind of fall into the, not the trap, but kinematics, if I remember correctly. I think that's what the term was, which means we're creating an equation that adds the forces that are being affected on Q2. So I'm going to write this little equation. I'm going to say, okay, here's the force onto the net force vector, right? So what I'm going to do is the way this is written, it goes like this. You have the first force onto due to 1. Does that make sense? So what this is saying onto due to 1, right? The force on 2, that is done by force 1, right?
That convention, or is that just how you did it?
That's the naming convention of these little sub numbers here.
Okay.
That's at least in the kind of example video that we had. That's how it is described as, because then we also have the force vector onto due to 3, right? Due to this Q3 down here. That's a messed up 3. Let's rewrite that. This is Q3. Oh, well. Okay. All right. So what this is going to do is if we want to solve it, this is how it goes. You get your net force. And what this is going to look like is these forces. This is just this down here. Boom. Right? So what this is going to do is this is going to become K. I kind of put it on top of the fraction in this instance, but let's think about this. We have K, we have the first charge, which in this instance, I'm going to have it be the particle number 2 multiplied by particle number 1. And then this is going to be the R squared that becomes the length squared, the length or the distance between those two particles. And then we just add that to K. Oh, can you guys see me? Whoa. You guys like disappeared from me here. Alrighty.
We can still see you.
Yeah.
Okay. That's good. Alrighty. This one becomes K Q squared, but not squared, sub 2. And then this is going to be Q sub 3 over length squared again. And if I remember correctly, if you want to be a little fancy with this, this is in like the I direction, I believe, because I is the Y, right? When you're talking about vectors.
I thought J was Y.
I, J, K. Oh, yeah, something like that. Ultimately, in the end, when you're writing this answer, it's not important. But I think you're right that it is J. We'll go with J. So what I did was just to kind of simplify it, because this is a lot of numbers to write. I kind of factored out some things. So what do these things have in common? The k times q sub 2 and then the distance squared. So I just brought that out. I did k q squared over L. And then this is q1 q1 plus q3. Now, this is where there's a little bit of, I describe it as a little bit of fuckery on the signs here, because here's the thing, right? When you multiply these two charges, right? Q2 and Q1, these, you're going to get a negative number here, right? Negative times a positive is a negative, right? So this is going to give you a negative. When you multiply Q2 and Q3, you're also going to get a negative, which will give you a negative. The problem that I ran into here was that we want to talk about this in regards to the perspective of the Q2 particle. So what I did was, okay, I want the direction of Q1 to be positive. If I'm pulling my particle Q2 in the direction of Q1, I want that to be in a positive direction, like mathematically. We see it here, but on the notes here, you're gonna get an increasingly negative number. That should be squared. So what I did was I kind of messed around with it. This is what I ended up doing. Oh, come on, let me move it. I made this negative Q1 plus Q3. Why does it keep messing up my threes? The reason being that when this multiplies and I get a negative number, this is going to become positive, meaning that if this particle is larger, it's moving we see it as moving in the positive direction on this graph. If it's smaller, this right here is going to give you a negative number. Then it'll be pulled more towards Q3. Does that make some sense there? I know it's a little convoluted, but.
So you made the F12 positive? Or F21, sorry.
This one, I made that one. I technically did this in a sense.
Because I'm not even gonna lie to you, I just calculate the force separately, like the magnitude, and then I just throw in negatives where because I just calculate the magnitude of the force, and then I'm like, nah, this should be negative. So I just put it as negative.
I kind of did that with some of the questions when it came to finding the amount of electrons that were added or removed. This is just kind of how I saw it done in his example. So I just kind of stuck by that one. So basically what you want to do here then is this is just plug and chug at this point. So this is going to be 9.0 times 10 to the 9.
And what'd you get for your final answer?
For the homework that I have, I got 0.67 newtons. But the thing is, this answer is going to be different because I used different numbers over here for the sake
I see.
Yeah. Then this is 3.6 times 10 to the negative 9.
And you kept 2 sig figs?
Yeah.
Cool.
Yeah. And then this is 2.2 times 10 to the negative 3. You guys see that I'm writing threes and it's like totally messing me up on that, right? Not just me. This is going to go negative.
Three.
Negative 2.0 times 10 to the negative 7.
I think you messed up one of your numbers. The Q3.
The
3.6. I think you must have looked at your other notes or something.
Oh yeah, you're right. That's the wrong number. Yep, negative 1.8 on that one. Oh, wait a minute. Wait, oh, hold on. I'm sorry. I'm messing this up now. Hold on. Q2. This is 4.0. Because this is Q2. 4.0 times 10 to the negative 9. K. Distance. Negative 2.0. 10.7. 10 to the 7th. Okay. Plus. Then this is Q3 here. Negative 1.8. Times 10 to the negative 7. 7. Yikes. Okay. And then this right here, I haven't done the math for this one just yet, but this is the right format here for Q1, Q3. Okay, so whatever answer you get there, that should be right. Now there's the question of, hey, what is the unit for this? This right here, I need to thank my chemistry professor a couple of years ago who hammered solving things symbolically. Because basically here's how we're gonna work this out, right? Because the Coulomb's was it Coulomb's constant, I think is what it's called. Or whatever. So let's remember that. So let me move this over.
Is it not just Newton's?
Yeah, it is in Newton's, but I was just going to quickly show how it's like, how it is Newton's. So we're going to take this equation. I'm just going to write the units for it, because this becomes Newton's times meters squared over Coulomb squared times, this is a charge. So that's a charge over the distance down here. So that's just going to be meters squared here. And then this is all times a charge minus a charge, which we can just treat that as a charge, right? So what happens is this cancels with that. This squared cancels with that. These cancel with that. You end up with Newtons. That's the last one. That's the only thing you get. So that's Coulomb's stuff, Coulomb's law a bit. Well, it's an application of Coulomb's law. That's one of the things with physics, is that you get like conceptual like functions, and then you have to apply it in really weird ways.
Mhm.
All right, let's see. Back to this thing. Electrostatic force, finding, this is just the magnitude. Comparing gravitational electrostatic forces. So in this instance, it looks complicated, but let's keep in mind that here's all he did. You have the net charge of the electron, the net charge of the proton. And then what he did is he then plugged in the distance, and then he multiplied it by, I think this is Coulomb's constant. And then he found you the net newtons of force. So let me whip out my handy dandy notebook. Ironically, when you think about it, in this instance, if you wanted to find the, I guess, like net attractive forces between these two particles, I'm pretty sure you would add the gravitational and electric forces together. Just because that's how that works. I'm pretty sure. But we can do this one together. So here's what I'll do. Just split it like that.
I mean, not to be like a terrible person, but it's just like, I feel like there might be better problems. Like, just like,
That's
I'm
valid.
looking ahead on the next couple of, like, not that I don't think it's important, but like, it might be better to do some like the harder problems, especially when we get to like the X and Y. I don't know.
Oh yeah, absolutely.
Maybe
Okay, yeah,
other
we'll
people
move
disagree,
on.
but
No, yeah, we'll move on then, because this one is pretty fun to just like rudimentary or whatever. Yeah. And don't ever feel rude by just saying, hey, let's do something harder. I think that's a good, like a good that's a good mentality we should have, I think. Like, hey, let's do something that challenges us more here, you know. So let's see. So we can't always neglect gravity in this sense. Did we do this one in class, or I think he just kind of glossed through this one, but oh, superposition principle. Right. Okay. I see. Gotcha. Vector addition. Is this the one that we were, where's the example question that we did? Was it this one? 6 point. Vectors are completely characterized by their components. Projections to coordinate. Oh, let's see if I can. Oh, it is. Okay. And then we ended on that one. Okay. So let's see. For the sake of finding the magnitude and direction of the net electrostatic force on Q1. Let's see. Do we have given? These are different things, and this is just symbolic solving. So this right here. Okay, let's see. Finding force vectors. This is different than the one that I have solved here.
There's one like at the very last slide that I think we might have done in class.
Q3. I have the notes for this one. I can solve this one right here if you guys would like. And it seems like this one, finding the magnitude and direction of the net electrostatic force on Q1. And it seems like that is pretty similar to this one. Just that you're finding, well, this one is a little bit more specific in terms of its coordinate system and whatever. Right. Do I have the solution to that one?
I think the only difference for the next one is you have to do like distance formula to figure out the distance between the points. But other than that, it like,
Yeah.
Oh wait, no. Isn't this the weird one where he like drew like 2 triangles or something? Or am I like,
I
guys
do
know what I'm talking
have
about?
one. I do have one like that. So here, I'll just kind of like write down what I have on my notes here. Because I don't know what this is in relation to though. Let me try something here. Let me like, ooh,
Yeah,
save.
that was definitely it. Because I remember being like so lost when he started drawing like 2 different triangles.
Yeah. I think that was in relation to superposition principle, because I have this in my notes here where it goes, you have, why is this
Wait,
so
isn't
thick?
that from Diffie Q?
Yeah, superposition principle we did do in Diffie Q. Yeah.
It's all coming back to me now.
So this is a particle here, in case you guys can't tell, and then it's an arrow. And then you have another arrow here. Superposition principle is basically like, here's what it says. It's just, I'm pretty sure you're just taking into consideration all kinds of, well, it says right here. This is vector addition. But he talks about superposition principle, that forces acting on a charge independently. You just add them all together, and then that's how you get the net force. Right. This was more fundamentals, but this is more like physics 1 stuff. You just want to take into consideration the X and Y axes type things here. And then you get, what is your theta angle there. And then this is your force. Let's just do the example question. All right, let's just do the example question. Let's not waste too much time. Okay. Example question. We're going to find the magnitude and the direction of the electrostatic force on Q1. So we have a particle right here. This is particle Q2. Particle Q2 has a net charge of -6.0. I think this is microcoulombs. And then this kind of goes down in a relatively diagonal direction to another
Is it
particle.
negative?
In my notes,
it
it
is.
is negative. Yeah.
Okay.
This is,
Yeah, I was just getting the next one. That's my bad.
yeah, Q1, this is going to be a positive 4.0 microcoulombs. And then this right here is Q3. Whatever, that's a 3. Okay, you guys can see that. Negative 5.0 microcoulombs. And this angle right here is 73 degrees. Now the distance here, R1 from R1 to 3 is going to be 0.1 meters. That was an M. What is it? Meters. Okay. Then it goes this distance right here, R1 to 2 is going to be 0.15 meters. So the difference that sets this equation apart from the one we did earlier was that in this one, we're trying to find the magnitude and direction of the net electrostatic force. The other one, we were just finding kind of like the addition of forces on the particle, like what the direction would basically be, the net force. So here's how this is going to work, right? So we're going to do, let's remember that, where's our equation? Here it is. The magnitude, so the magnitude, F, in this instance, here's what I'm going to say. I'm going to say F of 2 onto 1 is going to be, it's the same Coulomb's constant. That might be the wrong name, but I keep calling it that. Times, this is going to be the net charge of particle 2 times the net charge of particle 1, all divided by the distance between particles 2 and 1 squared. This one right here is something that you can, we'll solve it symbolically afterwards, I think, or whatever, but this right here basically becomes 9 times 10 to the 9th times, and then we're going to multiply by the fraction. It's going to be 4 times 10 to the negative 6. You might say, where did that come from? Let's keep in mind that we're dealing with microcoulombs. So that's why it's 10 to the negative 6. This is 4 microcoulombs. This is you're moving that decimal. Then it's going to be the same thing over here. It's going to be 6 times 10. Wait a minute. That. 10 to the negative 6. Now, these are magnitude forces. Oh, okay. So, sorry, I was just kind of stuck thinking for a second, right? But here's the thing. I was a little stuck because I read this and I said, wait, why is this positive in my notes? Because this is a negative 6. But we want to keep in mind we're finding the magnitude, which would be this to the square root of this number to the power of 2, which basically negates the negative. I just kind of like, I was taken back for a second. I was like, wait a minute, why is that like that? Times the distance between those two particles squared.
Wait, so I can't quite see your like math.
Oh,
never mind. That's my
zoom it
problem.
in.
So you're finding F of 2, 1.
Yes, the force of particle 2 on 1 is how you want to read that. So that's
Okay.
that's this right here.
I guess my question would be, so I immediately started this problem by, or at least, I mean, I'm not done with it, but figuring out
Mhm.
the X and Y components. So I'm finding the force on one in the Y direction, right? So that's only going to be caused by the only force on that is going to be the force between Q1 and Q2. So I'm just taking basically what you have, I think, times sine of theta.
Hold on. Let me get my calculator. Give me a quick second because I actually don't have it. Let me see this. Okay. Let me see, because I was under the idea. Let me see, X direction. 2-to-1, 9.6. Let me try something. Mode. So if we're talking about the X direction here, it's gonna be 9.6 times cosine 73. Okay, can you say what you said to me again, just to make sure I understood you?
Okay, so basically what I did is I'm trying to find the Y component of the force, right? So I took basically what you have, right? So K times Q1 times Q2 over R12 squared, but then I also took it times sine of theta, so I could find just the Y component.
Yes, no, that's right. That's the right way to do it.
Okay.
Just in the notes, we kind of have it like separated more in like a step-by-step sense, because I was gonna actually jump right into that afterwards, because you're right. The way we kind of write it down is it goes force 2-to-1 X is equal to the magnitude of the force 2-to-1 times cosine theta. And then it's the same thing for Y. Yeah, force 2-1 Y equals same thing, magnitude of the force to 2-1, and then this is times sine theta. Yeah, you're absolutely right. And your answers should be in the X direction 2.81, and then in the Y direction 9.18.
Just 9.18.
Newtons for the Y direction.
Okay. I don't know if I did something wrong, but I got 9.18 times 10 to the negative 18th.
Times 10 to the negative 18.
Yeah.
Well, because look, here's how this is how it should go, right? This should go. So the answer to this up here, this answer gives us 9.6.
Oh, wait. I'm sorry. I messed up K.
Oh,
We're
there
good.
you go. So this is 9.6 newtons. So all this really does is you do like 9 points. I'm just gonna write it here for the sake of notes and all that. 9.6 times sine, and then the angle is 73. And that gives you 9.18 newtons. Now, and it's the same process. This up here, man, this is messy. You guys got to forgive me. I'm writing with my mouse here. So, all right, let's see. Then we're going to do, oh my God. F of 3 onto 1. It's going to be the same process. This is going to be Q 3, and then 3 Q1, and then R, the distance of 3 to 1 squared. If you solve all that out, you get 21.6 newtons. What happens there? One of the things you want to take into consideration is in this instance, these are what's the word that I want to say? There is no y component to their kind of interaction, you know. So you only really have to solve this. Well, you actually don't really have to solve it in any sense, you know. So you can just look at this and say, okay, force of 3 to 1 in the x direction is going to be 21.6. Right. And then the force of that in the y direction is 0. There is no component of y in this particle, just because it's like literally right next to it, you know. It's a so if you want to do that, then you say f net x, and then what you do is you add you know, the x value, so you'd add these two together. Yeah, so I actually didn't write the answer for this one. The x component here is 2.81 newtons. So this becomes F21. What in the hell is that? 2, 1. There you go. X plus force 3, 1, X. And then that gives you 24.91 newtons. Right. And then you do the same thing for Y, which F net Y. That gives you 9.18 newtons. All right. This one is kind of like a bit of a more complicated. This is like, yeah, like just physics kinematics, I think. Physics 1 kinematics with this ugly formula. And you see, he kind of does it here in this example, where you're trying to find the magnitude on a Q1. And then you calculate the net force. So to calculate the net force magnitude, you just you get these net forces right here, and then you would do like the square root of these things to the power of 2. And that gives you the net magnitude force.
Okay, and just can we go over your x and y components again? I wasn't like fully listening. So we got the same thing for y, but what'd you get like for x, like the total force for x?
My total force was 24.91 right here.
24.91. Okay,
yeah,
I
so
did not get that.
Okay. So did you get, for the force of 2 to 1, did you get 2.81 newtons?
Force from 2 to 1, and we're saying the x direction?
Yes.
Okay. Wait, sorry, what'd you get again?
I got 2.81.
Yeah, that's what I got.
Okay, and then for the x component in force 3 to 1, I got 21.6.
I got 18.
18.
Yeah. So I
Now,
did 9 times 10 to the 9th times 4 times 10 to the -6 times 5 to the -6 divided by 0.1 squared.
Divided by 0.1 squared.
I feel like we did the same thing.
Now, did you do, for the x, did you like multiply it by a cosine value?
No, because it's already like it's in the same axis, so we don't have to do that.
Interesting. Okay, hold on. Let me
plug in my calculator again, just to be sure.
Wait a minute. You multiplied it 4 times 10 to the -6 times 6 times 10 to the -6?
No, so my numbers were 9, 4, and 5 on the top, and then 0.1 on the bottom.
9, 4, and 5, and then okay. I think okay, because this should be 9 times 10 to the 9th times Q3 would be 5 times 10 to the -6.
I keep them 18.
Okay, hold on. Now I'm gonna write this out. Let's see. Maybe our teacher had a little bit of a typo. Let's see. We don't know. Times 10.
Oh, wait, so you're
Mhm.
like taking it from like your class notes?
Yeah, I was just doing this for my class notes.
Oh, yeah. I don't know. Sometimes he does things and I'm like,
Yeah, that's fair. Okay, let's see. Times 10. So this is going to be times 5 times 10 to the -6. And then this is times hold on.
you can just like multiply the numbers together and then do the exponents. That's what I do.
Yeah, I'm just writing it out just like I need to visualize it. I'm a very visual person, so I need to times 0.1 squared. So with that, 9 times 10 to the 9th. Okay. Times the fraction. Wait, shoot. Times, and this is going to go 5 times 10 to the -6. 4 times 10 to the -6 times 0.1 squared. Huh. I'm getting 18 as well.
And I don't.
That's funky.
Yeah, I
Um,
don't know.
Did one of us like email the professor about it?
I thought you were saying that one of us did. I thought you were gonna say something else.
Oh no, sorry. It was a question.
9 times that should be this.
Or at very least, like ask the TA or something.
Do we have a TA? I didn't know we had a
Yeah,
TA.
we do.
Oh, okay.
But I don't know who it is.
Let me just I just need to look at this for a second. Give me a quick 0.1549.1 squared. Huh. I don't.
I mean, I'm just gonna roll with it because I kind of trust my calculator more than what he did. But like, if you guys don't, that's fine.
No, I agree. This should be 18. That changes a few things here. So that's gonna, if we're doing this, this is 18. That makes that a different number. So 18, that's good. This should be 20.81. And the y doesn't change because there's no y component to it. Okay, sounds like an honest mistake there. So there we are. Okay, perfect. Any questions about the math here besides that one, or what are we thinking?
And then for your net, did you get like 22.7?
For the net magnitude?
Yes.
Here, let me work it out. Let's see. So if I got 20.81 squared plus, and then this is going to be net y 9.18 squared, 22.74.
Yeah.
Okay. So this is literally writing 7.5. So in this instance,
22 if we did.
Yeah,
sig
yeah.
figs.
Depending on the sig figs, yeah. F net magnitude. Okay, that makes sense.
And even if we weren't doing magnitude, it would still be positive, right? Like, because it's all.
Yeah,
linking.
because
Okay.
yeah, with these charges, if we look at them, they're these are two negative charges So they would be pulling the positive charge, and they would both be in the positive direction. You know, if this is X positive, this is Y positive, yeah. I remember I hated like this kind, like that kind of framing in physics 1. It was like, well, it depends on how you frame it, and it was very frustrating. Wait, we
Real
just looked at
quick,
this one.
In I think that's the PowerPoint version.
Mhm.
But real quick, with that second slide 11, I think, with the slide 11 on lecture 2, why do we have to add that 180?
Let me look. Because if I'm right with this, the way I thought of this, right, was that you're looking at, so this right here, it's saying this is the force on one, no, from 1 onto 2. So you're looking at it like the force of here, the way I thought of it. Now, I don't know if this is absolutely right, but this is my logic behind it, is that because we're looking at the force of 1 onto 2, we had to kind of hold on, wait a minute. Actually, let's try something before I say anything. Let's try to big brain this a little bit. So this right here is a 90-degree angle. Wow, I love how it rounds out that edge. Amazing. Okay, 90-degree angle, right? Meaning that this is also a 90-degree angle.
Oh,
And then this should be this is gonna be 40, right? And then this is gonna be 30. Oh, this is a 50, this is a 50, right? So what we need to do is,
actually, I think I realized what it was.
okay, please explain it, because I'm burning my brain here.
Sorry. Because when you said the force from 1 onto 2, or you said 2 onto 1, you said something like
Yeah.
that.
Yeah.
I just realized that those are positive charges, and it's gonna have to be like it's going to be in like the down left kind of direction. So we need a vector going that way, and that's why.
Oh, they're, so they need them going to downward to the left position. Yeah, because they're repelling each other.
Yeah.
So that's what makes it negative. Interesting. Okay. That's a lot better than what I was gonna do. I don't know what the fuck I was gonna do. So,
I just realized it was positive, but thank you for going over that.
of course. That's actually, no, I'm glad you realized that, because that's a better logic here. This would have given you a positive number, but this is moving in the negative direction as a result. So you got to flip it down that way. So instead of the vector going that way, you flip it, like you said. That, I like that. Okay. Anyway, let's see, lecture 3. And then I think we could kind of start to wrap up, because I need to work on homework, and I'm working all of tomorrow. So continuation of that, continuation, the electric field. So this is one that I actually was a little bit late to class, so I struggle on it a little bit. Consider the number of interacting charges. We want to study motion of them under interaction with others. For many cases, we call the selected charge test charge, the other source charge. So the red is the source charge. The other ones are going to be the test charges. Electric field is the force exerted by source charges on a positive unit test charge. And then we have this graph, which signifies something. I don't quite know, but it does signify something. Dividing by QT gives the electric field at R. Okay. So all this person did was he removed QT from this equation, and that gives you the electric field at a certain position. Oh, okay, that makes sense. if the source charge Q is positive, the direction of the electric field vector is away from Q.
We also
if Q
assuming
is-
that Q0 is positive. Is that what we're doing in all these scenarios?
That's what I was just thinking here. I believe
I think so. That would make sense.
Yeah, because if you have two positive particles, the force is going to be in this direction as well as the magnetic field. It's almost going to be amplified in this direction because you have two positives coming in from there. And then you have a negative charge. Is there like a positive and negative particle simulator? I would love if we had something like that we could kind of like mess around with. All right. Anyways. But we kind of see that here. We have two like clouds of positive, I don't know, positive ions, let's assume. Superposition principle also applies here. So add up the directions of the vectors. So since E is a vector, you have to add E1 and 2, add the like forces, find the theta angle. This finding the angle that is used with the, what is it, like the tangent theta equals, what was the example question again? Something like that. Use it. For the net forces in the y and x direction. That's what it is. So to find the angle here, it's tangent theta equals the force net in x and force net of y over the force net of x. And then that's how you would do that. The figure shows two unequal point charges, little q and capital Q, of opposite sign. Charge Q has a greater magnitude than charge small q, in which the regions x, y, and z. In which regions x, y, and z will there be a point at which the net electric field due to these two charges is 0? So with this, I think we would just plug in. This is kind of a plug and chug here. And what we can do is this, like if we say this is like 0 and this is distance 10, you could say, oh, distance 1, what's the charge here? What's the charge here? And I think that's how you would find it,
I thought he said that for this one, there wasn't a point in which it would be 0. Like that's what I have in my notes.
Yeah, I would
And I think
agree
it's
with
because they're
that.
attracting to each other.
Yeah, I would agree with that because then positive has I would tend to agree with that. Yeah, I believe you on that one. 3 equal negative point charges are placed at the 3 corners of the square. Okay, this one I did not understand how he didn't go over it too much. But which of the arrows represents the direction of the net electric field at the center of the square? Would it be A? Just because like these kind of cancel in a way, and then this is the only one that's pushing, I think.
It would be C, because if you look back on the electric field going in the same direction as the force, we're treating the center as like a positive charge. So it would be the force from.
Oh, we're treating the
since
center
B
as a
and D
positive.
cancel out. Sorry, I was thinking back on the other one. Since the top left and the bottom right are canceling each other out, it would, since the vector B and D, sorry, it's an only night. Since vector B and D cancel out, it would be C, because that would be the only one attracting any positive charge from the center.
Okay, I think that's what I was missing. I didn't know we were assuming a positive particle in the middle of it. But I just thought that was for this right here. Positive point charge is fixed in position center of the square. As drawing shows, the second point charge is fixed at corner B, C, and B, C, and D. The second point charge is fixed at corner B, C, and D. The net electric field that results at corner A is 0. At which corner is the second charge located? Is the second charge positive or negative? Well, if we have charges at B, C, and D, yeah, A is 0. I don't think I understand the question. Okay,
For which one?
this one.
The first blue one. He said C, and then in class he said, in class he said negative, but I'm pretty sure it should have been positive. And then I went over this one
Yeah.
with him after class. He said the mass should be greater because the R is referring to the distance from Q, that charge, to any of the corners. And so from C to A is 2R. And because it's squared, our charge would have to be like quadruple the amount. So it would be a greater charge.
Okay, that makes sense. Okay. Man, I really wish you posted the answers. Okay. Then we have these. So the figure below determine the electric field in middle of the distance between charges. So with this here, I'm thinking we have Coulomb's constant. So with this, I'm thinking, do you guys have the answer for this one? Because I'm just gonna, because I'm thinking,
I might. Give me a sec just to find out.
okay.
Yeah, I didn't get it. In class, he said that R is 0.25, and I was wondering why it wasn't 0.5.
Because so instead of writing 0.5 squared, he just wrote 0.25,
Yeah.
which was kind of confusing, but that's just what he did.
I hate
Yeah,
that
I
he
get that.
skips a lot of steps.
Yeah. So would this be like Q1 times Q2
Okay, for this one,
over?
I don't have like the number answer, but I have the work that we did. And the only thing, so he had on his diagram that the electric fields were going in the same direction. Like he had E1 and E2 both like going towards Q1, which I did not understand at all.
Going towards, oh, wait a minute. Yeah, I think you're right. Hold on. I think I may have written this down actually.
Because I thought they would go in opposite directions, but I guess that must not be the case.
I'm assuming when we're referring to electron, what are we talking about now? Electron fields? Electric fields? What is happening? I'm assuming whenever we're talking about electric fields, we always have to assume that the point is positive and then it goes towards a negative charge.
Yeah, okay. No, okay. Okay, so wait, question. Do
Mhm.
do any of you guys have the answer to this question? By any
I
chance?
don't have the numerical answer, but I have the work. Like I have
Okay.
the work that we did. And so he kind of set it up. He said the total electric field was equal to E1 plus E2. And then he basically just like plugged in the equations for E1 and E2. And then where things started to get weird is he was talking about like the R hat vector.
Mhm.
And it quickly started to spiral from there for me.
Okay.
Because he said that R1 was greater than 0, but R2 was less than 0. And because of that, the second term, like the E2, is negative.
Okay.
I don't know why.
Uh-huh. I
Oh,
think,
wait. No, I think I do know why.
yeah, the assumption I have is that E2 is probably the positive and is probably pushing in the negative direction, maybe. That's all
I
I can
think
really
what,
think.
so I think his idea is that because these forces, like because the forces are attracting, they're adding to each other. And because E1 is negative, we'll also have to make E2 negative. That would be my guess.
Okay. Well,
And we could also make the argument that since it's attracting in the left direction, that might be why it's negative, but I don't know if that's like super physically sound.
Because they're both going in the left direction. So then one is positive and the other is negative, and that's weird.
are they both going in the negative direction?
They're both going towards Q1.
Yeah.
Oh. Oh, okay. Yeah. I could have sworn that I had at least the work for this. Let's see. Man. Okay. Okay. We can do this one. I have the work for this question right here. Here's what I've got. Okay. This is gonna be a lot of writing. Separated. So here's what we got to assume from this. So we have separated in a vacuum by distance of 3 meters. Find the spot on the line where the charges is net. Wait, where between charges where the net electric field is 0. Means that if you were to be put in that little position, you would not get pulled in any direction. So what we want to take into consideration, kind of like this equation we have up here, the electric field vector of the first electric field plus the second electric field is going to be equal to 0. Right?
Are you doing a different problem?
Yes, I'm doing this one down here, which I think is like somewhat like this top one, right? I don't have any of the work for the top one.
Okay.
Would you guys do you want to figure this one out instead, or
I don't have
you
the work.
guys-
Does anyone have the work?
Yeah, I mean, figure determine electric field in the middle of. Well, here, maybe if we do this one, we can kind of like look at it and see how we can apply it to this one. So let's see. Because what we want to consider is we have these two particles. We have a positive and then we have a negative. And then we have, this is a distance of 3 meters. And then because, here's kind of how I have it drawn, right? Well, actually it's here, exactly. It goes, you have this arrow, which is E1, electric field of 1. And then you have this arrow, E2. So then the formula that I have here goes kind of like what we had above. K times Q1 times distance square over distance squared. Now the thing is, because they're going to be 0, you just set them equal to each other because you're finding the spot where their electric fields are equal. Right? So Q2 over D squared.
But wouldn't one be the opposite of the other?
Or wouldn't one be the on 3 minus D squared? Wouldn't one be the opposite of the other?
Right, because if we actually had it equal to 0 and you were to like imagine in your head, like subtract 1 from both sides, like wouldn't one be negative?
I think the reason that we have it written like this is because we're talking about like the forces, not the direction of the force. I don't think, because we're trying to find where the force is equal. Because if the force is equal, they're going to cancel out, right? And so
you're saying worrying about magnitude, not direction right now.
I think so, yeah. In this instance, at least.
We're setting them equal to each other because it would be equal to 0 if we added them together, right? So if they were added together, they would equal 0, but one is the opposite of the other. Well, not added, they would subtract each other, right, to equal 0. So we're moving one to the other side, and so they're equal to each other.
Yeah.
It's like that K Q1 over D squared minus K Q2 3 over D squared is equal to 0. And then we're just moving one to the other side to make it equal to each other.
Oh, yes. Yeah. That's true. I didn't think about that. Yeah. So here, I'll kind of write out what you said. Let's see. So it'd be in this instance, it would be K times Q1 over D squared minus K Q2 over 3 minus D squared equals 0. So yeah, actually, you were right. What was your name again? Hold on. No, you were right on that one. You are subtracting. In this instance, it's just not super obvious, I guess. I need to have my coffee before I like do a study session, I think. That's what it is. In this instance, what we did was we put the equation in terms of D is what we did. So let's see. It's down here becomes D. Okay, sorry, had a text I had to respond to. D squared over Q1 equals, so we just flipped the things.
My question is, wouldn't it be easier to multiply everything through by D squared times the quantity of 3 minus D squared? Like, instead of like flipping it, can't we just like multiply it? Or is that just like not, does that just not make any sense?
You could. I think that the one thing is where that would get a little complicated is that you would be stuck with D squared times 3 minus D to the power of 2. And then you would have to, I guess, factor it all out and then try to solve for D and try to get D, but you have to get D by itself is the thing, so.
I just don't know how, like, I did not understand his algebra. Like, that was just like,
yeah,
I was lost.
I've seen some pretty funky things this semester in all of my classes with teachers doing some like really weird algebra, but here's what he ends up doing. Now here's what I'll say, right? I'll write this out. You try that version though, and let me know if it's like faster and all that, because I don't know. I just kind of go by what he says,
All right.
Because then you just square root everything. So then you end up with D and then square root of Q1, 3 minus D over square root of Q2. Then he splits it. D over square root of Q2. Okay. I see. So then, I mean, this is, yeah, D over Q1 plus D over Q2. And then D, factor out the D. And then you divide through skipping some steps and everything. Like you did, you get D equals 3 over square root of Q2. Oh wait, nope, I'm wrong. 3 over Q2. Never mind. I was
Okay.
1
I
over.
think my way, I did it and everything, and like the algebra, like it looks different from what he has, but it must be equivalent because I got the same answer. So
Oh, there you
Unless I
go.
just got lucky.
That's fair. The now here's what I'm a little bit confused, because in his notes he has this where it goes square root of Q1 is equal to 4 the square root microcoulombs. Which I mean, this ended up just being like this, right? This ended up just going, which I don't know how that works, right? But this became 3/2 over 1/4 plus 1/2, which that makes sense because you have your Q1, Q2, the square root of those is 1/4 of 1/2. And then you get 2 meters of distance. All right. Now, here's what I will say. The next PowerPoint talking about electric field lines and point charges. It's a lot. Would you guys be down to like do that another time?
Yeah.
I need to
Yeah.
finish the homework, and I got to get up at 7 tomorrow, and it's 10:30. So
Yeah, I was actually going to peer tutoring for this class tomorrow. So like if anyone else shows up, I'm gonna ask like I think his
Ooh.
name's Luigi to go over this.
Yes.
Please
Please,
go over all of the practice problems and the lecture.
Yeah, please drop those notes in like the notes chat or something, whatever you get, you know.
Okay.
I could use what I can get, you know. But all right. So that was a pretty good first study session, I think. For our first one. We can only improve from here. So I'll have to see y'all in the next one. I'll stop sharing my screen here. So I'll see you all, you know, if not this weekend, I'll see y'all on Monday. All right.
Yeah.
Sounds good.
Great.
All right. Have
See
a good
ya.
night, guys.
You
Yeah.
too.